Let's take a look at another example of a falling object, one that's launched straight up in the air. We've got Michael Jordan. He jumps straight up in the air in order to dunk a basketball. If he leaves the ground with a velocity of 4.75 meters per second, we want to know what his hang time is. In other words, how long he's in the air. Uh, Again, let's go ahead and make a table. We're only dealing with the vertical. We're looking at change in position, time, v initial, v final, and change in position. So we want to know how long he is in the air. Again, this is for the vertical. We don't have a change in position. We don't have a time. We do have an initial velocity. That is a positive 4.75 meters per second. Really, I don't need this. Meters per second. We don't know V final. We don't know change in position. Wait, I wrote change in position twice. I don't want to do that. What is my other variable here? Oh, acceleration, of course. That's going to be negative 9.8 meters per second squared. It doesn't look like we have a lot of information here. What we're going to do is we're going to think about what hang time means, time he is in the air, what that means. What that means is that he jumps up and returns back to the ground. So here he is. He jumps up to dunk the basketball. So he's up here when he's dunking the basketball, and then he returns back to the ground. So his change in position for the whole trip is, well, he starts at the ground and he finishes at the ground. So that change in position is going to be 0 meters for his change in position. All right, so at this point we need to take a look and see if we can figure out what equation we want. We've got change in position is equal to v0t plus 1/2 at squared. We've got v final is equal to v initial plus at. We've got v final squared is equal to v initial squared plus 2 change in position a. V initial, v0. We don't have v final. We don't have a time. In fact, that's what we're looking for. Let's put a question mark there. We do have acceleration, but I'm missing 2 things in this, so this isn't going to work for me. Again, I'm missing time. I've got change in position. I've got acceleration. Time isn't even in this equation. That's not going to help me, so this is probably what I'm going to use. So let's go ahead and go up here and see what we can get to work for us. I've got a change in position of 0 is going to be equal to v initial t. So v initial t would be 4.75 meters per second times time plus 1/2 times negative 9.8 meters per second squared times time squared. So let's see here. Let's go ahead and do this. I've got 0 is equal to 4.75 t. We'll worry about units in a few minutes here. Plus 1/2 times 9.8. It's going to be a negative 4.9 meters per second squared times time squared. I can subtract the 4.75 t over to the other side, so I get a negative 4.75 t is going to be equal to a negative 4.9 meters per second squared times time squared. Now, what did I put units back in here? I should just leave those out till the end. We know time should come up in meters per, or in seconds. So yeah, let's not even worry about that. All right, I'm going to divide both sides by t at this point. T and t, what happens is t goes away over here, and I get the t squared to cancel out. And I'm going to divide both sides by negative 4.9. And this goes away, and I get t is going to be equal to, uh, that goes away, so I get 4.75 divided by 4.9, which is going to be equal to 4.75 divided by, whoops, let's turn that on, 4.75 divided by 4.9, and that's going to be equal to 0.969 or 0.97. Let's go with 0.97 seconds. Spends almost a full second in the air. A couple of key things to remember here. Since he is launching and landing in the same spot, that change in position vertically is going to be 0, and acceleration is always negative 9.8 meters per second squared due to the acceleration due to gravity.